Hello and welcome to this video on solving problems. We like to call this the known and the unknown. So just exactly what is problem solving? Well, problem solving is a process we all go through every day, and sometimes we focus too narrowly on the idea that math problem solving equals an equation I just can't figure out. But this type of thinking not only limits your ability to solve problems, it also makes quote-unquote word problems the scary thing it is today. So coming to an understanding that you solve problems every day and that solving these math problems is very much like your daily problem solving will lower your anxiety about this process. Equations are often useful when solving problems, but it's not the algebra part that makes them useful. It's the organization of the knowns and the unknowns that make an equation useful. Once that is done, the problem solving is a snap. So basic problem solving is all about organization. And here are some basic steps for solving a problem that will work for any kind of problem, whether it's a math problem or a problem in your life. And your book's going to offer you some alternative ways for solving problems, and we'll even use some of those in some later examples. But it really boils down to just 4 things. So in step 1, figure out what you know and what you need to know. Now in step 2, assuming you have enough information to proceed, you have to organize what you know in a way that will help you find the solution to your problem. Now there are some problems where you don't have enough information to proceed and solve it. And there are some problems where they throw in a lot of extra junk you don't need to solve the problem. So you have to take the information you're given and organize it in a way that can help you find the thing that you need to know, the thing that you're trying to solve for. So you need to take the information you have and organize it in a meaningful way so you can sift through and figure out if you have enough to proceed, if you have extra stuff, and what are the things that you can do to find the solution to your problem. Once you're organized, now this is where most people make a mistake when they're trying to solve problems. They skip over step 2, and that is the organizational part. And when you skip that step, it is very difficult to solve a problem. You've got to do the organization first before you attempt to solve the problem. And once you think you have the answer, you have to make sure that your conclusion makes sense. Does it make sense in the problem according to all the information you're given? Sometimes it won't, and you'll just have to regroup and try again. You don't solve every problem the first time you try to solve it. Okay, so we're going to take a moment to just look at an example that's not a real mathy type problem, but it's a problem that needs to be solved, and it's something that we could encounter anytime. So it says you're on the bus on the way to a doctor's appointment, and then the bus breaks down. And the problem or the question that you have to answer is, are you going to make it to that doctor's appointment on time? Now, even though this is a purposefully vague example, it's going to help us think about the 4 steps and how we figure out what we know, what we need to know, how we can organize it, how we solve the problem, and how we can check to see if our answer makes sense. So our question here is, will I be on time? It's all about organization. So the first thing, figure out what you know, what you need to know. Well, you're sitting on a bus and that bus is going nowhere. You know that for sure. You know, have an appointment that's coming up. So you have to figure out if you're going to make it to the appointment on time. So you figured out some things that you know, and you figured out some of the things that you need to know, but you got to find out a few more things and organize it. So if you have enough information to proceed, you go ahead and organize it to see if you can determine your actual solution. So there's some stuff missing here. Obviously, you'd have to think about, what are the things that I should know here? So do you have information from the bus driver about when the next bus is going to come? Is it close enough to walk, and are you able to walk and make it on time? Can you phone a friend or a family member? How much time is left before your appointment? And did you leave with enough time to allow for an issue to come up? Or is it just too close to the time to actually make an accommodation to get there on time? So now we'll organize this information to solve the problem. We know the bus driver says it's going to be a half hour and the appointment's in about 20 minutes. So you know that's not going to work because by the time the bus gets there, your appointment's going to be past. You've called all your friends and family and you can't think of anybody else that you can call. Nobody can help you out and it's too far to walk. So you've come to the conclusion now that you're going to be late. So you've organized everything you needed to know in order to solve the problem, and now you've come to the conclusion that you're going to be late. Does your conclusion make sense? Does the answer make sense according to what you know? If it doesn't, you would regroup and try again. Well, unfortunately, with this given information, this is your solution. You're just not going to make it on time, and that's when you go into further problem-solving mode. You have to see, well, I have to call the doctor's office to see if I can come in later today, or maybe I'm going to have to change to another day. So we're continuously solving problems and reorganizing our thoughts and getting information from others so that we can solve problems. And this is something that you do every day. So the bus example is given to show you that you solve problems every single day, and you don't even think about it, you just do it. Why is that so easy? Because you've been doing this kind of problem solving your whole life. You've had experience with organizing these kinds of situations, and some people are better at that than others. So all you have to do is take the ability you already have to solve all kinds of life problems and transfer that over to solving other kinds of problems. And believe it or not, what you already know will help you to solve math problems, and what you learn about solving math problems will help you to solve these kinds of life problems. And I know what you're thinking, but I hate these useless math problems. And I've never been good at these useless math problems. And I just don't understand why I have to do these useless math problems. So you need to stop. Because all problem solving is valuable, no matter what kind. From video games to Sudoku puzzles to doing your family budget to these useless math problems, these all exercise your brain. That makes you smarter. And any experience you get from any type of problem solving transfers to other areas of your life. Your classes, your job, your life as a consumer, and especially your life as a consumer. So repeating to yourself that you hate the problems, that you're not good at the problems, and that you don't understand why you have to do the problems is going to just create a wall between you and your potential to solve these kinds of problems. This kind of negative talk limits your ability to think clearly about them because you're just too busy thinking these wasteful thoughts. So it's time to kind of get over the idea that you can't solve the math problems and buckle down and recognize that you are capable of solving these problems. And so you ask yourself, well, if I'm bad at it, how do I get better? Well, it's not a secret. Experience plus practice equals learning. So if you get experience with these kinds of problems and you practice them, you will learn how to do them. And the more you practice, the easier it is to solve the problems. If you already knew how to solve all the problems in the class, you wouldn't need to take the class. But this is what's called learning. And anytime you learn something, there is a struggle of sorts. How many times do you think somebody who is as talented and fantastic as LeBron James is at basketball practiced basketball when he was a kid? And how many times do you think Bill Gates, the guy who created the software that created the background for this video, how many times do you think he failed before he found something that worked? You don't think that Steve Jobs and Apple created the iPod, the iPad, or the Apple computer without putting a little time and effort, do you? All kinds of problem solving involve a struggle, and they involve a commitment of your time and effort. So embrace the struggle and practice. If you do, you will get better. Not just at math problems, but at solving all kinds of problems. So let's look at some of these examples. This is your experience. Then you go and practice and you get better. Here's our first problem. Can it be solved? What's missing? Sarah makes $8.50 an hour. How much will she make this week? We know she makes $8.50 an hour. And we want to know how much she makes this week. And we know that to find her weekly pay, we need the rate that she makes times the number of hours she worked. So can it be answered? No, we don't know how many hours she worked. So there are some situations where you have to pursue additional information before you can solve a problem. So before we can figure out how much she's going to make, we have to figure out how many hours she's going to work. And then we would just multiply to find the answer. Second example, what's irrelevant? Too much information. Michael's going to buy a new MP3 player, so he's been saving his money. He saved $10 a week for 11 weeks. The MP3 player cost $140. How many more weeks does he have to save at the same rate to have enough saved to buy this MP3 player? So what do we know? Michael saved $10 for 11 weeks, so he's got $110. And what do we need to know? Well, we need to know the difference between the price and what he saved. So he's got to have $140, he's got $110, and so he needs $30 more. So at $10 per week, there's 3 more weeks that he has to save to come up with the $30 to have enough. So what were we given in this problem that was irrelevant? Actually nothing. We really needed everything that was given here in order to find out how much more he needed, except we really didn't need to know that it was an MP3 player. It could have been any kind of a purchase. But in terms of the numerical information, we needed it all to solve the problem. So sometimes there will be irrelevant information. This is not one of the cases. So in terms of the math, you have to figure out, what do I do? And so sometimes there are keywords or phrases that help you figure out the operations you need, and we discussed some of those previously. There are a couple more I want to talk about. The first one is the better buy. And sometimes you will be asked to find between these two items which one is the better buy. So this is called unit cost comparison, or cost per unit. That is the total cost divided by the number of units. And in order to compare the prices of two items, they have to be broken down to what's called unit price. So we'll get an example of this in just a minute, but just remember that unit cost is the total cost divided by the number of units of the item. And again, just a reminder that per means to multiply, such as the pay per hour. Pay per hour would mean that you multiply. And also remember that sometimes you just have to use trial and error to solve a problem, and there's absolutely nothing wrong with that. So if you don't get it right the first time, you get an answer that absolutely doesn't make sense, go back, check your arithmetic, look at your operations. You could have just made a careless mistake. So we're going to look at a couple of consumer problems, and this goes back to that better buy concept that I was talking about earlier. And we want to know which of the following is a better buy. Now we do this, those of us who have to do the grocery shopping in our families, or the shopping of any type, we do this every time we go into a store. Now unfortunately for us, the stores make it purposefully difficult for us to do this. So when you look on a shelf, they put the cost per unit sometimes, but they don't compare equal things. For example, you might see 2 brands of toilet paper on a shelf, and one may say the cost per roll is 50 cents, and the other may say the cost per sheet is 2 cents. Well, then you'd have to do math to calculate and figure out which one of those is still the better buy. So in order to find a better buy, you have to be comparing like things. So in our first example here, we've got a 64-ounce bottle of juice. It's $5.76, and 128 ounces of juice, that's $12.16. So we want to find the unit price, and in this case, our unit cost is going to be the cost per ounce. So you've got to compare the cost per ounce. You've got to be comparing two things that are exactly alike. Now, the cost per ounce, I'm going to organize here, $5.76 for 64 ounces. Now remember that to do cost per ounce, we'd have to multiply the unit cost times each ounce. So something was multiplied by 64 to get 5.76. That was our unit cost. So to find unit cost, you have to divide the total cost by the number of ounces. So if we take our $5.76, need a decimal point in there, and I divide that by 64, take my calculator to do that, and I get 9 cents. So the 64-ounce bottle of juice is priced at 9 cents, and that's 9 cents per ounce. Now, the second one, we know the total cost is $12.16, and we know there's 128 ounces of that juice. And so again, because cost per ounce has already been multiplied out, we have to divide the total cost by the number of ounces, and we do that, and we get 0.095. As a consumer, if your major concern is not the size, but it's the price, you would need to go with brand A, because it is 9 cents versus 9.5 cents. And just as a reminder, let me show you how you write 9 cents with a dollar sign. It is a dollar sign, 0.09. If you want to write it with a cent sign, it's 9 cents. It's not 0.09 cents. It's the dollar sign with the decimal. The cent symbol, there's no decimal included. So our second example, remember again, we're looking for unit cost, and that we've got a total cost for a can of green beans. So for A, we're going to take $2.58, divide it by 20. 258 divided by 20, take your calculator out. 0.129. That's 12.9 cents. Almost 13 cents. Calculate the second one. Unit price, $3.68 divided by 32 ounces. Using my calculator, that's 0.115. This is the lower cost. In this case, choice B is the better buy. So when you're trying to find the better buy, you have to take that total price and divide it by the number of units. So take total cost divided by units, and that will give you the price per single unit, and then you can compare the single unit prices. It's not possible for you to compare when you're not comparing like things. So you have to get it down to the same thing first. So in both cases, we got the cost per ounce, and then we could pick the better price because we were comparing the cost of an ounce to the cost of an ounce. So here's a personal or consumer problem, something that you as a consumer may encounter. A new computer system can be bought off the shelf, tax included, for $1,200. If you don't have the cash, though, you can pay $150 down and 20 monthly installments of only $70. And so if you decide to take that installment plan, how much more will you pay? Depending on your situation, you may say, well, I don't have the $1,200, so I'm going to have to go with the installment plan. That's also what people do with credit cards and get into a lot of trouble. So if you got the cash, you can pay that one time. But if you don't have the cash and you've got to buy it in installments, you've got to pay in a different way. $150 initially and 20 payments of means to multiply $70. So I want to compare these two things to each other. Now, what happens with your down payment and your installment payments? Well, eventually those all add up to what you paid for the computer. Do your multiplication first. You got your payments. So you end up, under the installment plan, paying $1,550 or $350 more. Now, that might be worth it to you. If you put that $1,200 on a credit card and then pay that over time, you might even end up spending more than the $1,550. But you have to make a good decision here. What's best in your situation? So you have to be able to compare these two kinds of plans to each other. So here's an income problem, and here's another example of having to compare like things, or what you may hear some people say as apples to apples, not apples to oranges. Compare apples to apples, like we did with the unit cost. We compared ounces to ounces. Here we know that Jonna makes $72,000 per year as a high school assistant principal, and that Keisha makes $6,400 per month as a middle school principal. And we want to know who makes the most and by how much. Well, we're not comparing two things that are the same. This is per year, and this is per month. So we've either got to convert Jonna's salary over to monthly or Keisha's salary over to annually. And you can do it in either order. And you can do it either way. Now, the easiest way is probably to take Jonna's salary, $72,000, divide that by months, so we can figure out how much she makes per month. That's $6,000 per month. That means the per means you'd multiply. You'd have to multiply that 6,000 times 12 to come up with that 72,000. So we have to do division to figure out what her monthly salary was. Well, we already know the answer now, that Keisha makes more. She makes $400 a month more. So Keisha makes $400 per month more. And since she makes $400 per month more, that would be 400 times 12, or $4,800 more per year. And so what you could do is now you could figure out actually how much Keisha makes if you wanted to. She makes $76,800. And the way I got that was not by multiplying 6,400 times 12, which I certainly could do, but by just adding the extra that I know Keisha makes to what Jonna makes. And so that made it easy for me to come up with the $76,800. So Keisha makes more, $4,800 a year, or $400 a month. Here's another consumer example. 6 friends are getting together for a vacation trip to the Grand Canyon. They plan to rent an RV, and the RV they plan to rent, excluding the gas cost, is going to be $240 a day, plus $3 for every mile they drive. We need to find the cost each friend must pay for the 10-day trip that covers 1,920 miles, and we want to make sure that each friend pays their fair share. In other words, that everybody pays the same amount. Now, we got quite a bit of information here, so let's see if we can organize this. And here's kind of an example of how you might really want to organize when you have a lot of information. So I'm going to start by thinking about what I know and what I need to know. So let's just organize our information into what we know. We know that it's $240 per day. We know that it's $3 per mile. We know that it's 10 days. And we know that it's 1,920 miles total. Now, there's one other thing we know, and that is that there are 6 friends. So that's going to help us at the end figure out how much each one of them has to have. So there are 2 parts to this problem, and that is the amount they pay per day and the amount they pay per mile. So we've got the daily charges plus the mileage charges, and that's what we need to figure out, and then we can figure out how much each of the friends have to pay. So $240 per day, 240 times 10 days, plus $3 a mile, 1920 miles, so you just take your calculator out and you multiply these guys together. 2,400 added to, multiply out the other part, 5,760, comes to a total of $8,160. That's for everybody, though. So if we want to know how much each friend pays, take our 8160 and we divide it by 6. Because we want to know the cost per friend. Now remember, cost per friend implies that we multiply to get this total cost of 8160. So in order to figure out the cost per friend, we have to divide. That comes up to $1,360. Now this one's complicated enough that I think you ought to double check to make sure that it makes sense. So I'm going to go through a checking process here on this problem, even though we haven't done it before and probably should have, but let's do it on this problem because it's got a lot of details here. So we figured out the total to be $1,360 per friend. So I'm going to kind of work backwards here and see if our answer is right. We said we've got 6 friends, so 1,360 times 6. There's your 8160. So we've come to this 8160. Now that part makes sense. Now let's double check to make sure that we came to the 8160 under the right conditions. 240 per day. Well, there's the 240. 10 days. That's where we got the 2,400. And $3 per mile. Well, there were 1,920 miles. So that's where we got the 3 and the 1,920 for the 5,760. So our 8,160 is the right amount. Now, if this part's wrong, then this part's going to be wrong. So it doesn't hurt to work backwards to make sure that your answer makes sense and it fits with the arithmetic. Here we're presented with a tax problem. A business purchased a vehicle for $84,000 that was worth $63,000 after 3 years. The business has to report the value for tax purposes each year and claim the depreciation amount as a loss. Now, this is a good thing for a business. They have an asset on the books, such as a vehicle or a computer or some other machine, and each year its value goes down, so they get to claim that against their assets so that they don't have to pay as much tax. So assuming that the loss in the value is the same every year, how much is it losing each year, and what will be the reported value in the 5th year and then in the 10th year? Now this is one of those exercises where a table might be necessary to help you organize yourself. So let's write down a few things here. So I'm going to write the numbers 0 through 10 here, and one thing I do know is at the very beginning of the first year it was worth $84,000, because notice that it was purchased on December 31st. So I've got $84,000 at time 0. I also know that it's $63,000 3 years later. And so now that we know this, we want to know the value in the 5th year and the 10th year. Well, in order to figure out those later years, we have to figure out how much it's decreasing by every year. We know the difference between when it was first bought and 3 years later, but we don't know the amount per year. But we do know it was 3 years later, so we can find that. So if we take the amount that it's lost and we subtract, we know that this loss was for 3 years. So it's losing $7,000 every year. Now, if that assumption is correct, we should be able to subtract $7,000 from every year, and our chart should make sense. So if I take away $7,000 from $84,000, I get $77,000. I take $7,000 from that, I get $70,000. $7,000 from that, that's where the $63,000 comes from. So yes, it's going down by $7,000 each year. Subtract $56,000. Subtract again $49,000. $42,000. $35,000, $28,000, $21,000, $14,000. So we continue to subtract $7,000 for every year that it's lost value. And we've created our table here, and we can answer our question just based on this table. We could do some other kinds of math to solve this, but we have our information organized in a table, and we can answer our question just by looking at the table that we've created. So the loss is $7,000 a year. At the end of the 5th year, it's worth $49,000. At the end of the 10th year, it's worth $14,000. Okay, so here's a problem about making change. JC paid for her order at Big Burger with a $5 bill, and her order total was $4.15. Now, in the change drawer, there are 5 nickels, 4 dimes, and 2 quarters. How many different ways can the cashier give her change? And what is the least number of coins that can be used to do this? So now we're going to have to organize ourselves in order to do this. And I think the easiest way to do this is let's just make ourselves a chart of quarters, dimes, and nickels. So once again, we're seeing that the way to solve a problem has to do with how we organize our information in the first place. And if we start with the least number of coins, we're going to see a pattern, and we can go down from there to find out how many ways change could actually be given from this change that's in the drawer. So, 85 cents. That's our change. $, decimal point 85, or 85 with no decimal and the cent sign. Means the same thing. 85 cents. If we're going to give the most quarters possible, we'd like to give 3. That'd be 75 cents and a dime, but we only have 2 quarters. So we're going to have to give 2 quarters. That gives us 50 cents. We got 35 cents left. So if we give 3 dimes and 1 nickel, that's going to give us 50 cents here, 30 cents here, 5 cents here, 50, 30, 5, 85 cents. So that's certainly one way. And since we started with the biggest coins, that's going to be our least number of coins. Now, there is another way to make this change, though, still using the 2 quarters. That's still going to be 50 cents. But we've got this 35 cents that we could do in a different way. Let's say we don't give the 3 dimes, we only give 2 dimes. Well, that's 20 cents. So we're up to 70 cents. We've got to get to 85 cents. We need 3 nickels to do that. We can do it one more way. Let's give 2 quarters and only 1 dime. 2 quarters again is the 50 cents. 1 dime is 10 cents. That gives us a total of 60 cents. We need all 5 of those nickels to give us the 25 cents to make this thing work. So here we have a problem that's called a shortest route problem. And so today you have several things to do, including going to the bank, to the pharmacy, and to the dentist. And our question is, given this map of the directions and distances we can go, what is the shortest route from home, making all 3 stops and returning home? So the first thing you have to think about is to organize this information in a way that will help you to understand all the different possibilities for your trip. If you start at home, you can see that there are 3 choices when you first start out. You can go from home to the pharmacy, from home to the dentist, or from home to the bank. So those are our first 3 initial routes that we could go. Once you pick your first route, for example, if you pick the pharmacy route, then you have 2 other choices. So if you go to the pharmacy first, you have 2 choices for your second route. So I'm going to go ahead and write in pharmacy, dentist, and bank again, because on your second route from the pharmacist, you could go to the dentist, or from the pharmacist, you could go to the bank. So I'm going to make sure I record this properly here, with the dentist following the pharmacy and the bank following the pharmacy. And so then we think about, well, if we went from home to the dentist the first time, so from home to the dentist, there'd be a couple of choices there as well. We could go up to the pharmacy, or we could go down to the bank. So from the dentist, we could go to the pharmacy, or from the dentist, we could go to the bank. Now, our third choice of initial routes is to just go to the bank first. So if we go to the bank first, we still have 2 options. Go over to the pharmacy or go to the dentist. So from the bank, you can go either to the dentist or the pharmacist. It doesn't matter which way you do this. So we'll say from the bank to the dentist, from the bank to the pharmacist. And then you have to look at, from your second stop, what's your third stop. So from the second stop, you'll have 2 choices as well. So if our second stop was the dentist, so here we have the dentist in our second stop spot, we could either go to the pharmacy or to the bank. So it doesn't matter which one you do first. From the dentist as our second stop, we could go to the pharmacy or to the bank. And with the pharmacy as our second stop, we could go either to the dentist or the bank. Again, with the pharmacy. And if our second stop is the bank, then we can also go either to the dentist or the pharmacist. So just make sure that all of your routes are covered here, and there actually turn out to be 6 distinct routes that you could take. Now, once you know the route that you're going to go, all you have to do is total up the distances so you can figure out which one of these routes is the shortest route. So with the first one as an example, from home to the pharmacy is 6.3, and we're assuming here we're in miles. And from the pharmacy to the dentist is 3.2. So I'm just picking up these numbers from my route. From the dentist to the bank, 6.7. And then from the bank to home would be 9. So the total of this first route is what you get when you add these 3 numbers together. So pause the video for a few minutes and go through and add up these numbers and see what you get for these routes. And once you've done that, start the video again, and then you can see what the sum of the routes are, and from that we can pick the shortest route. Okay, so now if you've added up your routes properly, you would see that the first route is 25.2 miles, followed by the second, 25.6, and then so on. And if you look, you'll notice that there are 2 possible routes that you could take that would give you the least distance or the shortest distance to make all 3 stops and return home. So the first one would be from home to the pharmacy, from the pharmacy to the dentist, from the dentist to the bank, and from the bank back home. The second one would be from home to the bank, from the bank to the dentist, from the dentist to the pharmacy, and from the pharmacy back home. Now, if you look at this picture, you can see that these are actually the same routes. They're just traveled in opposite order. And so 25.2 miles is the shortest route that you can take, given that you have to stop at all 3 of these places and you have to return home. This problem is called the magic square problem, and actually it's not really magic, it's just math. Now, these so-called magic squares have been around for over 4,000 years, and in some cultures they're believed to have astrological or divine qualities. Their usage ensuring a longer life and prevention of diseases, and therefore they were used in paintings or engravings or sometimes on jewelry, so they were thought to bring you health and prosperity. And in a magic square, the sum of all the rows, so that's in this direction, all the columns, that's in this direction, and the diagonals, which would be this way and this way, have to equal the same value. So sum meaning you have to add them up. So from the given information, we can now find the missing values. And the first thing we have to do is figure out what our magic square number is. And in order to do that, you pretty much have to have all 3 numbers in one direction or the other. And we can see along our diagonal, 23, 24, and 25 is going to tell us that our magic square number is 72. So in each case, our columns, rows, and diagonals must add up to 72. Then we can take a look at that first row and see, well, if we've got 23 and we've got 21, well, that's a 44. So in order to find A, we take 72 minus 44, and that's going to give us A is 28. And we just work our way around here and we can find the other values of our magic square. Now that we know the 2 numbers, 28 and 24 in the middle, we can go down and we can find that number, and we work our way around. So if you'd like to pause the video and try to find the values of B, C, D, and E, you can come back and take a look at the actual answers in just a minute. So I hope these are the numbers that you got. If not, you should go back and check your arithmetic. You may have heard of the game Sudoku before, and maybe you've even played it. And yep, this is math too. In this game, the digits 1 through 9 must appear in every square and in every row and every column with no repeaters. So in each one of the squares, you have to use all 9 digits, and you have to make sure that you don't repeat in any row or any column. So we'll just do one of these squares, and then you can pause the video and see if you can complete the whole thing. So I'm just going to start by saying I see a 7 here and a 7 here. Now I know that there cannot be a 7 in this square because that would put a 7 underneath another 7, and we're not allowed for that. I know that there can't be 7s here or here, so I know that this has to be a 7 because there has to be a 7 in every square. So I've got my first number completed, and now I'll just continue until I can get one square completed. And you might see some things that I don't even see. I see these 3s here, so I know 3s can't go here, 3 can't go here, 3 can't go here. This guy's got to be a 3. Now I'm going to look down in the square where I've been successful and gotten a number, and I'm going to look at this 7 that's located here and this 7 that's located here. Knowing a 7 can't go here and a 7 can't go here, I know that that has to be a 7. So you can see how I'm just kind of working myself around, knowing that I've got to pay attention to what can and cannot go in certain places. So I almost have a completed square. So I'll think about the numbers that I need for that bottom square. I need a 1 and I need a 5. So I'm going to take a look and see if I can find that 5. Well, you will notice there's a 5 here. That means 5 can't go there. 5 has to go in this spot, meaning 1 has to go in this spot. So I have completed one of my Sudoku squares. Now, if you'd like to pause the video and see if you can complete another square or yet another, the answer is going to be on the next screen. And if you like to do this kind of puzzle, on the next page I'm going to give you a website where you can print these out. It's really a great way to pass time if you're waiting in a doctor's office or something and you need something to do to sort of pass time. So pause the video, see if you can do at least one more square, and then look at the answer on the next screen.